Stein's lemma. So it essentially, this lemma tells us that this exponent of this hypothesis testing um, is given by the quantum relative entropy. Okay, so this is the very well-known quantum relative entropy, and this holds for every epsilon. So it doesn't really depend on the kind of epsilon in the definition of the asymmetric error. Now, I want to stress here that before this result in 1991, the quantum relative entropy did not have an operational meaning. Okay, so this is the result that actually gave a justification for the use of quantum relative entropy. And I think this is a bit surprising because if someone learns about quantum information theory now, everyone is just kind of takes the quantum relative entropy for granted. We always assume it's the right entropy to use, but that was not the case. There was a long time when we didn't really know which how to define a proper generalization of relative entropy to quantum systems. And this result showed us that actually it is this kind of the well-known quantum relative entropy. So the first operational meaning of the quantum relative entropy was as the exponent in hypothesis testing. And okay, so it's to understand the same problem for the case of symmetric hypothesis testing, it took several more years to compute this, but it was also found that the exponent for the symmetric error, the symmetric hypothesis testing error, it is given by this quantity called the Chernoff divergence, which is defined using this optimization problem. And this is also a computable formula. So we have an exact formula for this asymptotic exponent, but it was already quite difficult to evaluate this quantity. And these two results essentially together constitute a complete solution of the very basic setting of quantum hypothesis testing of two fixed quantum states. But in practice, we encounter much more complicated settings of hypothesis testing. And unfortunately, these results have not been generalized much. So to give some examples, for example, a very commonly, or in some settings, an important problem is the generalized Stein's lemma. It's called also it's known as composite hypothesis testing. And here we have that the error is essentially is the hypothesis, the second state is not just a single state, but it can be any state from this set of states F here. So essentially, we quantify here the worst case error. We want to discriminate one state rho versus a whole set of states F. And now then we ask, what is the best exponent we can get? The best error exponent. And this question is unsolved for this composite setting, except for some special cases. It was claimed to be solved by a paper of Brandao and Plenio, and it was a very fundamental result, but unfortunately it was found to be incorrect. So right now we don't have a solution to this problem. So that is a kind of a very fundamental open question in quantum hypothesis testing. Another case is the discrimination of quantum channels. And I will get back to this later, so I don't want to define things here yet. But when we talk about discrimination of channels, essentially many things are unknown. And for example, we don't know a Chernoff kind of bound for channels. These kind of quantities are unknown when we want to discriminate quantum channels. So these extensions of the results of the quantum Stein's lemma and the quantum Chernoff bound are actually very difficult to obtain. But okay, so this concludes the kind of introduction to the basic setting of hypothesis testing. I would like to introduce now our framework that we propose as a slight modification of the setting of hypothesis testing. So here is the basic setting that we've just talked about. So we have a measurement and we guess either rho or sigma, and we make a small change in this setting. We allow an additional outcome. So now if we get outcome 1, we guess rho. If we get outcome 2, we guess sigma. And if we get outcome 3, we say, I don't know. And this might seem like a very natural thing to do, yes, but this setting, the original setting, it doesn't allow us to say, I don't know. We have to guess either rho or sigma. And before I go into the kind of the mathematical details of this setting, I want to give you some intuition for when we would like to use such a extension. And this is actually a very natural extension, I think. So For example, assume that you have some particle detector, and this particle detector it detects it is supposed to distinguish between the state rho and state sigma. So it's supposed to tell you if it's rho or sigma. But now imagine that you send some particle through this detector, and it doesn't detect anything. So what do you do? Well, there is nothing you can do in the original setting of hypothesis testing, because you have to make a guess, rho or sigma, but you cannot make a guess. So it's kind of like a strange situation. And exactly in our setting, now we can say, I don't know. My detector didn't work. I don't know. That is a natural case where we can use this kind of extended setting of hypothesis testing. Another case is when we want to minimize the error, the probability of making an error. And the easiest kind of case to imagine is when you go to a doctor and you ask the doctor, do I have cancer, or do I have some disease? And the doctor runs some tests, but it's not conclusive. He's not completely sure. Okay. So if this doctor is doing usual hypothesis testing, he has to tell you, yes, you have cancer, or no, you don't have cancer. But if he's wrong, then both of these are very bad for you. So the doctor doesn't, he wants to minimize the risk of being wrong. So if the test is not very conclusive, he will rather tell you, I don't know, than try to guess, of course. So that's a natural way to understand where this kind of setting could come into play. But okay, so let's now try to understand this at a kind of more formal level. So we have this measurement. We have three outcomes of this measurement, and we denote the measurement operators as M1, M2, and this M question mark. Now, to understand how we define these error probabilities, I want to step back and look at how we define the original conventional hypothesis testing error probabilities. And we can rewrite this type 1 probability and type 2 probability as the probability of error given that the state is rho and the measurement is m. Okay, this is just the original definition of the type 1 error, just kind of rewritten in this kind of probabilistic way. And so following this idea, we extend this definition to this setting of this extended hypothesis testing, but we want to avoid this third measurement outcome, because this doesn't tell us anything. Okay, we can only make a guess if we get M1 or M2. So we want to avoid this inconclusive outcome. So we define the conditional type 1 error and the conditional type 2 error as the probability of error that we given that the state is rho or sigma here, and the measurement is m, and the measurement is conclusive. So we disregard this third measurement outcome. So what this looks like is essentially just the original kind of the usual definition of type 1 error, but then we have to divide this by the probability that we get the conclusive outcome. So we just get these kind of quantities. And I think this is a natural definition. If anyone has any questions or any kind of things, please do stop me and you can ask at any point. Okay, so this kind of definition is, okay, this is asymmetric definition. We can also go into yes. So when we define the optimized asymmetric error, then we do it in the same way as before. We define the minimize overall measurements, but now the measurement are all three outcome measurements. So we minimize the conditional type 2 error such that the conditional type 1 error is less than epsilon. And this is given by this optimization problem. Yeah, so in the symmetric setting, the original definition of the probability of error was essentially the minimal probability of error given m. That's just the basic definition, because it was the average, and this is essentially the average probability of error is precisely this. So we do the same thing essentially. We define this conditional probability of error as the probability of error, but conditioned on the conclusive measurement outcome. So what this is just the ratio of the probability of error versus the probability of conclusive outcome, and we get this kind of quantity. And now, of course, what we want to do is we want to characterize these quantities, and they do look more complicated than the original definitions, but we will see that the opposite is true. The opposite is true. these are actually much simpler than the original definitions of the error. So that's what maybe the surprising result here is. But to understand these quantities, we have to introduce first the notion of the max relative entropy, because this will be kind of entropic quantity that will find use in understanding these kind of what we call post-selected hypothesis testing errors. So yeah, so the max relative entropy D max is defined essentially with this kind of inequality. The inequality is where in terms of positive semi-definite matrices. So we are comparing two different states, and essentially we're asking how much bigger one state is than the other in the context of positive semi-definite cone. This can be evaluated exactly. This is not like a difficult optimization problem. But okay, so this quantity gives rise to two different metrics on the space of positive operators, at least. One is the Hilbert projective metric, and this we denote this as d omega, and this is just the sum of d max of rho versus sigma plus d max of sigma versus rho. So it's kind of like a symmetrized version of d max. And the Thomson metric is denoted like this, and this is the maximum of the two. So instead of summing up, we take the largest of the d max of rho versus sigma and sigma versus rho. Okay, so these two quantities, they found use in a lot of geometric papers, geometric concepts and results, but not much in quantum information until recently. The Hilbert projective metric was defined in one paper by Reeb and collaborators, but after that, it didn't find use until only last year. So it was a bit unappreciated, I think. Yeah, but a crucial property of these two that we will be using is the fact that they are additive. So it's a very simple property because it follows from this kind of definition of the max relative entropy. They are additive. So if we have tensor products of states, then these quantities will be just n times the original quantity. Okay, and so given this, we can finally get to the main results. And yeah, first, the asymmetric hypothesis testing, which is the equivalent of the quantum Stein's lemma in the conventional hypothesis testing. In this setting, what we show is that the exponent of this conditional type 2 optimized type 2 error, the exponent of this error, it is given exactly by the Hilbert projective metric. Okay, so this, you might remember, this is exactly the equivalent of the quantum Stein's lemma, but in the original setting, in here we had the entropy, the quantum relative entropy, but now we have this max, this Hilbert's projective metric here. But we don't just establish like a similar result. Actually, we show something much stronger here, because we establish a formula not just for asymptotics, but already for essentially for any state. We can show that the error, this optimized type 2 error, is given by this function of the Hilbert projective metric. So what this means is that this can be evaluated for any state, and in particular, if we take n copies of states, you remember that this is an additive quantity. So this thing is very simple to evaluate. We can exactly compute the error for any number n any number of copies n. And the interesting thing here is where we have the additivity, and then when we want to compute this for n copies, we can easily bound it from, essentially we can just rearrange this expression, and then we can get essentially bounds that show us very easily how this will converge to this this Hilbert projective metric. But one thing you might notice here is a very interesting property, because in conventional hypothesis testing, okay, we know the asymptotics, we know that the exponent is the relative entropy, but actually it is very difficult to understand, or at least more difficult to understand, how fast the convergence to this exponent happens, or essentially, because in addition to these kind of like the linear terms, the kind of terms that asymptotically matter, we have many lower order terms, and these lower order terms, they can affect the convergence speed, but they are much more difficult to characterize. In this case, there are no lower order terms. Okay, in the upper bound, lower bound, everything, the only n dependent term here is this one. There's the only linear dependence on n. Everything else is n. It doesn't depend on n. So if we just divide this by n, essentially we get a convergence depending only on this one function. So this is a much simpler case than the conventional hypothesis testing. Essentially, we can understand not only the asymptotics, but even the kind of the one-shot case and everything in between. We exactly can characterize the convergence from the one-shot to asymptotics. And I want to actually go through a quick sketch of the proof because it's quite simple. For this first result that we have is quite simple. So if you don't follow, don't worry. This will not matter later. But just kind of to give you an idea, if you're interested, we have this expression for this optimized type 2 error of the post-selected error, the conditional error. And this looks a bit kind of maybe scary, but there's one thing we can notice immediately is the thing that this condition here, that M1 and M2, they have to be essentially less than identity. This is completely irrelevant. Why is it irrelevant? Because if this is not true, then we can simply renormalize these operators. We can divide them by their norm to make them less than identity. And this division will cancel out because we have fractions in the left-hand side, right-hand side. Essentially, we can divide them by anything we want. So the kind of the normalization doesn't matter here, and we can completely ignore this constraint. So what we can do is we can write now. Okay, I will write in the inverse of this because this will be a bit easier to work with. We can write this as the following optimization problem. And okay, it still looks a bit ugly, but if we just rearrange this expression, and I don't want to show this, it's just algebra. If we just rearrange this, what we get is that this is actually we have this kind of epsilon factor here, and then it's just like a ratio of m1 with rho, m2 with rho, and then we have m1 of sigma, m2 with sigma. Okay, and these kind of fractions we have here. Okay, this maybe looks a bit nicer, but doesn't immediately look nice, I guess, and it's not obvious what this actually equals. So to understand what this equals, we have to look now at the Hilbert projective metric. As you might remember, the Hilbert projective metric is the sum of the Dmax. So essentially, if we take the exponential of this function, then we get the product of these two, and this is this optimization problem. So this is like a pretty simple optimization problem, and it can be shown quite easily to be a convex optimization. And we can take a dual problem of this convex optimization problem. So we can compute the dual form of this, and this is also very easy to do. And we obtain the following problem. And now, if you look at this equation and the previous equation with the star, you might notice that they are actually the same. They are the same thing. And there's more, obviously, this kind of these ugly factors of epsilon here, but except for this is the same optimization problem. So these two are actually equivalent, and we get the claimed result, which is that the optimized error in this post-selected, the conditional hypothesis testing, is given exactly by the function of the Thompson projective metric, and from this we get the asymptotics, as I've already showed you. So that's it essentially for the proof. Yeah, it will be a bit more difficult to generalize this proof to other cases, but the basic idea here I wanted to stress is is a nice, simple application of convex optimization. And one nice immediate extension that we can obtain is the composite setting, so the generalized Quantum-Stein's lemma, which you might remember, it is essentially we optimize the error, but with this we take the worst case error, the worst case type 2 error, optimize over all states in some set F. So F is some fixed set of states. So what this is we maximize over all states sigma in this set this error essentially, and we want to understand the exponent, so the asymptotics of this. So the result we obtain is that for every convex and closed family of sets of quantum states, the exponent actually equals this Hilbert projective metric, but we have to essentially regularize it. This is called a regularization. So this we essentially we take this Hilbert projective metric and then we minimize it over the set F, and we take the limit as n goes to infinity with row tensor n. So these kind of quantities are very commonly encountered in when we deal with composite hypothesis testing. So this is actually, well, natural to be expected. But the crucial thing here is that this result, such a result, is not known in the conventional hypothesis testing. So we don't have an equivalent result to this one. And so we were able to compute this exponent exactly for the post-selected setting that we are here, but we don't know how to do it for the conventional setting. So that's why it already shows you how this kind of this setting simplifies some proofs that are very difficult to do in the conventional setting. And the proof, I don't want to go through the proof in detail. It is a bit longer. Essentially, it follows the same idea as before, but now we have to use the duality of this optimized, this problem optimized Hilbert projective metric, and this we can use a result from a recent work of mine. Right. So of course, the next step is to look at the symmetric setting. So the symmetric setting, the Chernoff setting. And in this setting, we obtain in a kind of similar manner that for every states, for every prior probabilities, the post-selected probability of error, the symmetric probability of error, is given by a function of the Thompson metric now. So previously we had the Hilbert projective metric. Now we have the Thompson metric, which you might remember is the maximum of the Dmax of the max relative entropy. And yeah, so we have an exact result for every state. And again, we can use the additivity of this function to conclude essentially that when we have n copies, what happens is that we get this kind of expansion. And as n goes to infinity, the only thing that will matter here is this part. Essentially, we can disregard completely the P and Q. So that the prior probabilities will not matter at all. And we obtain, again, that the asymptotic exponent for the symmetric hypothesis testing is given by the Thompson metric exactly, and there are no lower order terms here again. And yeah, so this is this essentially is the second fundamental result, because this is the equivalent of Chernoff bound in quantum information. So in the post-selected setting, we obtain this Chernoff result in a much simpler manner. And we show that it equals this Thompson metric. So the interesting aspect is that Thompson metric did not have an operational meaning in quantum information theory, and even that the Hilbert projective metric it didn't have an exact meaning in state discrimination. So in this work, for the first time, we give an operational meaning to these quantities, such as this Hilbert projective metric and the Thompson metric, because we identify them exactly with these kind of exponents. But we don't stop here. We want to go further. We want to find more things. So in order to go further, we look into the much more difficult setting of quantum channel discrimination. And in quantum channel discrimination, we are given a channel now, an unknown channel, and we know that it's either M or N. It can be one of these two channels. But now, to discriminate channels, we can do much more than before. We don't just plug in a channel to a measurement. What we can do is we can prepare an entangled state. We can plug in only a part of this entangled state to this channel, and then we can do a measurement on this kind of joint system. And then from this measurement, we get again.
Sorry. Hi.
Yes. So is there a question?
Hello.
Yes.
Okay. I have a question.
Yes.
So, I'm a little bit confused. Why is post-select? Because so the goal is to discriminate like rho and sigma, and then okay, I forget the name. Like you calculate like this loss beta thing, and then you say, okay, then I can compare the cross entropy like D, the between rho and sigma.
Mm-hmm.
It seems I can just from the state itself, then I can know how I can discriminate these two states. then why is called post-selected?
Why is it called post-selected? Okay, to understand this, we have to go back a bit. Maybe I should clarify this a bit better. Post-selected means we disregard all these inconclusive measurement outcomes. This means we post-select on the measurement outcomes being 1 or 2, essentially. That's in post-selection just means that we disregard some outcomes of the measurement. That's what it effectively means in this case, at least. And I think in most cases it means a similar thing. We essentially we ignore all the inconclusive measurement outcomes. So, for example, if you do this in practice, what happens is if you run this measurement and you get this inconclusive outcome or outcome 3, you just ignore it and you run it again, and you keep doing it until you get a good outcome. So that's how it is done in practice. It is a very simple procedure, I guess, to do in practice. You just repeat the protocol, but of course you might have to repeat it many times. But the point is that you essentially ignore whenever you get a measurement outcome 3, and you only keep the data for the measurement outcomes 1 and 2. And this is essentially post-selection, and yeah, that's why we call it post-selected hypothesis testing. Does this clarify things or not?
Okay, thank you.
Okay, yeah, if there's any more questions later, we can discuss. Yeah. So going back to channels now, we have a similar setup, but I mean it's more extended now, because now for the channel we can we can optimize essentially, or we can choose any input state. We can plug in any input state and also optimize over the measurement. So now we are optimizing over input states and measurements. And this setup is the most general way to discriminate quantum channels. So again, we use the setting of post-selected hypothesis testing. So we have this additional outcome. But now, okay, so we have to clarify how we define the errors here, because of course we can define the errors naturally. Essentially, we optimize the error of distinguishing these two. Essentially, these are states, right? At the end and the output of the protocol, you get a state, because you just to clarify, at this point of the protocol, it is a state, because it is a state that went through a channel, but here we have a state, and then we measure a state. So essentially, we can apply the result from a previous, from the first part of the talk, which was concerned with states, but we have to apply it to this kind of, we have to apply it to the channel only on a part of a system. We have to optimize over these larger entangled systems, and we have to choose the best such state. So this seems more complicated. And if we want to understand these in terms of these two quantities I described, the Hilbert projective metric and the Thomson metric, we end up with these two complicated quantities, because this is essentially it looks like we have to optimize over all input states to understand these kind of errors. And this is a difficult problem potentially. However, we can show that we can avoid this completely, because to compute these quantities, we actually only have to evaluate only one state. Only one state. We can choose this row always to be the maximally entangled state. So it is sufficient to evaluate these two quantities, that the Hilbert projective metric and the Thomson metric, for the choice state of the channel. So the choice state is the channel applied to the maximally entangled state. And this gives us exact formulas for the error of the conditional error and of asymmetric hypothesis testing and the symmetric hypothesis testing of quantum channel discrimination. But the issue is, again, that we only had one copy of a channel here. We only allowed one use of a channel. And in practice, this is not how it's done. But in practice, it is actually very complicated to discuss how to discriminate many copies of channels. Why? Because there are many different ways in which channels can be used, because a quantum state, when you have n copies of a state, is always tensor product of n copies. For a channel, not always. We can use channels in n copies as a tensor product. This is known as a parallel strategy, when we just use essentially like a tensor product of n channels. But we can use much more general strategies, and this is called an adaptive strategy, where we essentially uh, we we apply this channel once, then we do some processing, and then we can use this knowledge to make a better guess, I guess, or to make maybe choose a better state, for example, to plug into the channel in the second round. So we can use each round to improve our kind of strategy in the next round. And it's known that these adaptive strategies usually can do better than parallel ones. Not always, but in many cases they can do better. So it is always necessary to characterize also these adaptive strategies. However, even these ones are not the most general strategies, because, for example, it is known that we can use phenomena such as indefinite causal order. And I don't want to get into detail about this. I just want to kind of quickly visualize this plot I stole from a paper, but this shows a so-called quantum switch. So a quantum switch is a simple kind of procedure where in this setup, we can either apply this channel first and then this one, or this channel first and then this one. And essentially, these two are in a superpositions of causal orders, and it is known that this can actually give advantages over adaptive protocols in some settings. So it is also important to understand if we could improve using this kind of more exotic protocols, for example, indefinite causal order strategies. And in general, these are difficult questions to answer because we would like to understand the exponents for all such different strategies. So what can we do? Well, it's easy to define parallel strategies. A parallel one is just we apply a tensor product of channels, and this is kind of the basic definition of the error of between channels. But when we want to characterize more general protocols, we have to find a way to define what is a general protocol. Okay, and let me make for now a very weak assumption that this protocol, I use the letter epsilon to denote this protocol. For every protocol that essentially manipulates or discriminates n channels, it has to take n channels and it has to turn them into some positive operator or quantum state. You can think of it as a quantum state because we have to get a state at the end to measure it. So essentially, I want to stress this is a very weak assumption, because everything we do with quantum channels, it has to preserve the positivity, the kind of physicality of these channels. In practice, when we manipulate channels, we assume many more things. This is only the very basic assumption. But what we will do here is we will only take this assumption as our definition of the protocols. What I mean by this is we will define the error, the best error, using any protocol as essentially the minimal error by when we optimize over all protocols of this type. And this is defined for asymmetric and symmetric setting. And I want to stress that even if these protocols are not physical, every physical protocol is a subset of these. So this gives us always an upper bound on physical protocols. This is the idea. I'm not saying they are all physical. I'm saying that whatever protocol you can imagine, it has to be a subset of these protocols. That is the basic idea. And interestingly, what we show is that for all channels, there is no advantage gained by using such general protocols over parallel ones. So no matter what protocol you use, you cannot do any better than parallel ones. And this holds for any number of copies. So it's not only asymptotic result, it's for any number of copies. Whatever you do, whatever fancy protocol you can imagine, in this post-selected setting that we have here, you cannot do any better than parallel ones. So parallel ones are always optimal. And this parallel ones are actually very easy to characterize. So it's very good for us because we can compute exactly the exponents, and the exponents are given. We can just use the results from quantum states that we had to essentially to exactly compute the exponents here. And yeah, the exponent for asymmetric setting will be the Hilbert projective metric between the choice states of the channels, and the symmetric exponent will be the Thomson metric between the choice states. Now, this result is much stronger than all known results for channel in conventional discrimination. For conventional discrimination, there's no such strong, for any n, equivalence between parallel protocols and more general protocols. Uh, for kind of these results, for conventional hypothesis testing, for example, you can see that our result doesn't depend on the epsilon. Okay, we can always ignore the epsilon, but for a conventional hypothesis testing, we only know what happens when epsilon goes to 0. So that's known as a weak converse bound. What we have here is a strong converse bound, which means that it holds for every epsilon. And for this symmetric error, nothing is known for the conventional setting. So we don't have an exponent for discriminating quantum channels in the conventional, the non-post-selected setting. But in this post-selected setting of this work, we can compute exactly. And yeah, and the proof idea essentially is just to use the results from states to get an upper bound. And then to get a lower bound, we have to use some properties of the max relative entropy of quantum channels. So with this, we just kind of cite from a previous work. And then we argue that because of that, essentially, you cannot do any better than parallel strategies. By any kind of strategy, you cannot do any better than parallel ones. And essentially, we have to get equality there. So the proof is reasonably straightforward once you have all this in place. Yeah, so this kind of, I hope, shows you that the results we get for channels are go much beyond kind of conventional hypothesis testing. And one other extension we can do of our results, and I'm not sure if many people are familiar here with general probabilistic theories. I won't go too deep into them, but the point is that in many cases, it is interesting to study theories beyond quantum mechanics, because there is no guarantee that quantum mechanics is the kind of the ultimate physical theory. And it's interesting to see, for example, what happens if we change some assumptions, or what really is needed to recover quantum mechanical properties. And general probabilistic theories or GPTs, they generalize quantum theory, classical theory, and more general kind of abstract probabilistic settings, in which everything we could imagine. And mathematically, what happens is that positive semi-definite matrices, or quantum states, the cone of quantum states, is replaced with a general convex cone C. So we have some cone, we don't know anything about it pretty much. The measurements are operators in the dual cone of this cone, and then essentially this, I'm obviously simplifying here, but with these two kind of with the choice of a cone, essentially we can define a GPT. And for GPTs, for hypothesis testing, not much is known, and exponents have not been computed in general. But what we can show actually is that all of the results I mentioned about quantum states, they actually hold the same in GPTs. So without any additional assumptions about the GPT, we don't have to make any restrictive assumption. We don't have to essentially constrain ourselves to any kind of subset of GPTs. We recover the same results. We can recover the same exponents. And I only mentioned these two results here, but also the non-asymptotic results. Essentially, everything we showed for quantum states, it holds the same for GPTs. And things like the Stein's lemma, for example, or the Chernoff bound, they are not known for GPTs at all. They are only known for quantum mechanics and for classical probability theory. But for everything in between and everything beyond, nothing is known. And here for the first time, we compute our exponents, which apply also to GPTs. Yeah, and I apologize if people don't care about GPTs here. Just kind of this, like just a further extension. That's what you can think of it. Yeah. Yes, and this essentially this is it for the results. I wanted to briefly conclude what I talked about. The first, thing I want you to remember is that we introduced here the novel setting of post-selected hypothesis testing, and this setting, I believe, has not even been characterized in the classical case. So we talked with some classical information theorists, and we asked them if they knew of anything like this. They said no, no one seemed to have ever looked into this. So we believe that no one has really defined this kind of approach, even in classical hypothesis testing. But if I'm wrong, then please feel free to correct me. Okay, so in this setting, we evaluated all possible optimal error probabilities. And this is what I mean by this is that we evaluated them both one-shot and asymptotic probabilities, both for asymmetric and symmetric setting, and both for quantum states and quantum channels. So essentially, every kind of combination here you can imagine, we computed it. And importantly, we managed to compute them even when in the conventional setting, nothing is known about these results. For example, the composite quantum Stein's lemma, the generalized quantum Stein's lemma, is not known. What equals the exponent? What is the exponent for the conventional setting? But we can compute it exactly here. And also the Chernoff bound for channels and the kind of a strong converse result for channels, we get essentially very easily in our framework. And kind of maybe the surprising thing is that the remarkably simplified proofs compared to the standard approach. Essentially, everything here simplifies a lot, and we were able to show results. Essentially, in quantum hypothesis testing, people spend decades working on this. On for example, the Chernoff bound. It took many years to prove. The Stein's lemma. It took many years to prove, and somehow we got results here almost for free. Like these results are once you get the basic results, essentially everything else is not too difficult to obtain. It's like a very simple kind of like a follow-up. And that is the kind of the interesting property, because essentially we managed to simplify the whole framework of hypothesis testing just by making the small change. The only change we made here essentially is to allow this third outcome, this third measurement outcome. And once we allow that, everything simplifies. So that is the remarkable property of this kind of setting, I believe. There are open questions, of course. One is, for example, in hypothesis testing, not just the Chernoff and the Stein kind of exponents matter. Also, there's a whole family of exponents which kind of essentially generalize and connect these Stein and Chernoff regimes. And it will be interesting to understand this also for this post-selected setting, but we have not been able to do that yet. And of course, we only characterized the case of two channels or two states, which is probably the most fundamental important, but nevertheless, it will be interesting to understand, for example, what kind of balance we can get when we have n states or n channels. And with this, I would like to thank you very much. You can enjoy this summary table. Thank you.
Thank you. Is there any question from the audience?
I have a question. Hi, Bartosz. This is Hao Chung. Thanks for this very nice talk. I have a question. So as we know that the conventional quantum hypothesis testing can be used to characterize many quantum information processing protocols, I'm wondering what kinds of quantum information protocols can be characterized by your post-selected quantum hypothesis testing?
That is a good question. I should have included the reference here. I didn't include this. We have a paper actually also recently because we realized that this quantity can really especially this Hilbert projective metric.
Yes.
It can really play the role of the entropy in many different settings.
Yes.
So, for example, we were able to show that it plays the role of entropy when we talk about transforming quantum states. So, for example, entanglement distillation.
Yes.
Entanglement distillation is understood in terms of the entanglement entropy in conventional setting, and in our case, it's understood in terms of this entanglement Hilbert projective metric.
Okay.
And the only change we have to make there is we have to allow essentially probabilistic protocols.
Oh, okay. So that's the one you gave in Beyond ID.
Yes,
okay.
exactly.
Okay.
Okay, yes. Good that you know that one. Yes,
Yeah.
yes. So precisely. So that is the connection we make, because originally we found that was the first result we found actually.
Mm-hmm.
The first result we found was the Hilbert projective metric as the kind of a rate of transformation between quantum states, like an asymptotic rate, but we have to allow not just quantum channels, but kind of more general probabilistic maps, and then we get this kind of rate. And now we found essentially, I think, a much more fundamental property of these entropy quantities, these kind of the Hilbert projective metric and the Thomson metric, as the error exponents. But if you're asking what else can be done, I don't know how far we can push it, because I mean, I'm sure that if you take some protocol, some quantum information protocol, and you relax some assumptions, you allow some probabilistic things, you might be able to get a quantity of this type.
I see.
I don't want to say you can do this for every protocol, but maybe you can do it for many protocols. I don't know. It would be interesting to investigate, but I mean, it's not interesting to do it like, one by one. I think we have to find a nice way to show many protocols at once. And for this, I don't have an answer yet, but I mean, it's a very interesting question to study. Yes.
I see. Thank you. I'm mostly interested in a channel coding case, so maybe let's.
Okay, we can discuss this. We can discuss this definitely.
This is very interesting. Okay, and I have another question. So in conventional quantum hypothesis testing, the Chernoff bound is actually equivalent to the Hofding bound. If we have a Chernoff bound, we can directly obtain the Hofding result, and vice versa. So, but here you can obtain the Chernoff bound, but you mentioned that the Hofding is missing.
I think I know. So I don't actually remember how you get the Hofding bound in originally. However, I think I might know one problem. Yeah, because essentially, conventionally, this average error, this symmetric error is the average of the asymmetric error, essentially.
Yes, exactly.
And this helps simplify this kind of asymptotics. But for us, it is not the case. So you see that the asymmetric error is defined as this fraction. But this one, it is not average of fractions. It's a fraction of averages.
Okay.
So because of this, it becomes a bit more non-trivial to understand the asymptotics of like the connection between the two, like how one goes to the other. So I think this is what prevents an easy proof of the Hofding inequality. I think from a discussion I had with Mark about this, it might be possible to go around this somehow, but I would prefer if maybe, I mean, it's just maybe different. Maybe it's more interesting to do it. Maybe we have to find new methods, which is always better than just doing these old things the same.
It's good to know the difference.
Yeah, but I think at least there is a non-trivial step that has to be done here. So we don't have an answer yet to that question yet.
Okay. Okay, thank you very much. And I have no questions.
Thanks for the great questions here.
Do we have any questions? Okay. Okay, I don't think we have any further questions in the audience, but I only have like one small comment. So remember that you also mentioned that this post-selective hypothesis testing hasn't been done in the classical literature. I think in the quantum case, there's a similar task that's called state discrimination, right? And in the state discrimination, there's also a setting that they call unambiguous.
Yes.
And
yes.
There was done in, I think, 2003 by this MIT student.
No, this we fully acknowledge this in the paper. This I didn't mention in the talk. But what people did there was essentially only symmetric error and only one shot.
They also do not consider post-selection, so they did not quotient out this don't care result. But I think they might raise this interesting question whether this post-selected state discrimination, what the optimal formula would be. Because I don't think anyone consider post-selection state discrimination yet, at least to the best of my knowledge.
Yeah. Yes. Unambiguous is a bit different because you want error to be zero, essentially.
Yes. Error to be small. Yeah. And they can. I think the result is the optimal solution can be given by semi-definite programming, so it's easy to obtain. So that's why it's
Yes.
interesting.
Yeah. So essentially, what I meant is maybe no one has looked into error exponents in the setting of post-selected discrimination. I think there was a time in like 2003, as you mentioned, 2003, maybe until 2009, where people looked into kind of similar questions. But we went through all of these papers, and no one really studied exactly what we are doing here. I mean, there's always a chance that some random, Russian did it in 1962. This happens often. So, I don't want to claim we are the first ones, but maybe no one has looked into this.
Yeah. Okay, good. So thank you very much. We could talk more since we are fairly close, Taipei and Tokyo.
Yeah. I mean,
are you with Mio?
Yes, with Mio right now. Well, I mean, yes, with Mio for now. Yes. Later, I don't know, but I'm for now. Yes.
Okay. Good. Cool. So let's talk more.
Sure. I mean, I would like to definitely to catch up at some point.
Okay.
Thanks a lot for the invitation, and yeah.
Okay, thanks for the day. Bye. Bye.
Thank you. Bye.